map from C, the universal curve, to MG, F. And a natural way that we can make classes on the moduli space of curves is as follows. We'll start with omega F, which is the relative canonical of F. We'll take its first Chern class, raise that to some power, say I plus 1, and then apply the F push forward to this class. That'll give me something in codimension I on the moduli space of curves, and we'll call that class kappa I. And then I'll define the tautological ring of MG, denoted R star of MG, to be the subring of the Chow ring, which is generated by the kappa classes. And there's a lot of work and conjectures surrounding the relations that the kappa classes satisfy. And it seems that this tautological ring is highly structured. Another nice feature of the tautological ring is it's thought to include most geometrically motivated classes. So if you have some intersection theory question that's motivated by geometry, hopefully it would be answered by some calculation in the tautological ring. In general, the Chow ring might be much larger than the tautological ring. In fact, for large genus, there's no reason to expect even that the Chow ring is finitely generated. However, it is known in small genus that the Chow ring is actually generated by tautological classes. This is work of the several authors I've listed here, and they've shown that the Chow ring of MG is tautological for G less than or equal to 6. On the other hand, there's a very striking theorem of Van Zelm, which says that in genus 12, the fundamental class of the bi-elliptic locus in the Chow ring of M12 is not tautological. So here, a curve is bi-elliptic if there exists a degree 2 map of the curve to E, an elliptic curve. So in light of these two theorems, I think that a natural question to ask is the Chow ring of MG equal to the tautological ring in the remaining intermediate small genera between these two theorems? So this would be for G equal to 7, 8, up to 11. The main result I'm presenting today, which is joint work with Sam Canning, answers this question for genus 7, 8, and 9. We have shown that the Chow ring of MG is tautological for G equal to 7, 8, and 9. In these cases, the tautological ring is actually already known by work of Faber. So Faber's work is implemented in a SAGE package called ADM cycles. And we also used an extension due to Pixton to compute the Chow rings listed here. So in genus 7, we see the Chow ring is generated by kappa 1 and kappa 2, mod these 3 relations. In genus 8, also generated by kappa 1 and kappa 2, mod another 3 relations. And in genus 9, we need the first 3 kappa classes, and they satisfy these 5 relations. And Faber notes that genus 9 is actually the first example where the tautological ring is not a complete intersection ring. And he also notes that each of these cases satisfy his conjectures concerning the structure of the tautological ring. So this answers our question for genus 7, 8, and 9. But it still leaves open genus 10 and 11. And in light of Van Zelm's result about the bielliptic locus, I think a natural question to start with in that direction is to ask, are the fundamental classes of the bielliptic loci in genus 10 and 11 tautological? And on this front, Sam and I have been able to show that yes, the fundamental class of the bielliptic locus in genus 10 is tautological. And in genus 11, I'm going to write maybe here. We have some work in progress that we hope will be able to answer this question. So the key new results that Sam and I have that allowed us to prove this theorem for the moduli space of curves in genus 7, 8, and 9 is intersection theory on low-degree Hurwitz spaces. And I'm going to explain how this comes up and what some of the key difficulties are in proving this result. So our basic approach to this problem is going to be to stratify the moduli space of curves by gonality. So stratify just means cut up our space into pieces we can deal with one at a time. And gonality is an invariant of a curve that I'll define now. It's the minimum k such that there exists a degree k map of C to P1. And it's a fact that the gonality of C is always at most G plus 3 over 2. And equality holds for the general curve. So here's my picture of M7 or M8. The gonality goes all the way up to 5, and the general curve has gonality 5. And I'll list here also in genus 8 the codimensions of the curves of special gonality. So in codimension 2 is where we see the curves of gonality 4. Then the curves of gonality 2, they're more special. They occur in codimension 4. And even more special is gonality 2, which occurs in codimension 6. And then here's my picture of M9. The gonality goes up to 6. So throughout, I'm going to write mg with the upper K to be the following locus. We take all of the curves in mg so that the gonality of C is equal to K. And then we're going to take the closure. So this is the same as all of the curves of gonality up to K. So in terms of my pictures, this would be MG4. And now our goal is to show that all the classes supported on MGK are tautological modulo classes supported on MGK-1. If we do that for all K, then we'll know that all classes on MG are tautological. Now, it might sound like I haven't done that much yet, but this is actually quite helpful because it breaks up our problem into some more manageable size pieces. And I'm going to illustrate that to you by starting at the bottom of this stratification. And a key fact that we'll use, which is due to Faber, is that the fundamental class of each of these MGKs is tautological. So in K equals 2, these are the hyperelliptic curves. And this stratum is the same as the space of 2G plus 2 distinct points on P1. Because the hyperelliptic map is unique, and you should think of these 2G plus 2 points as corresponding to the branch locus of that degree 2 cover. This space, in turn, is just projective space of dimension 2G plus 1 minus the discriminant locus modulo automorphisms of P1. And from this description, it's not too hard to show with rational coefficients that the Chow ring of MG2 has no non-trivial cycles in positive codimension. So it just has its fundamental class.
Why is it 2G plus 1, not 2G plus 2 in projective space?
So we're looking at, did I make an addition error here? We want, yes, sorry, that is correct. Thank you. Right, so we have this description of MG2, which is quite explicit as a quotient. And from it, we saw that there's only the fundamental class supported on this locus. And so we know the fundamental class is tautological, so everything here is tautological.
Oh, sorry, is that P1 to the 2G plus 2 power?
This is, I want to take polynomials of degree 2G plus 2 in two variables, and then I want to look at them up to scaling. But then I want to remove the polynomials that have a multiple root.
Okay, thank you.
The
Yeah.
points are unordered.
Yes, thank you. Yeah, not marked, not ordered. Yeah. Any more questions? Yeah, so this is kind of the baby case of this whole procedure. All right, so I'll go on to now k equals 3. So we're going to look at mg3 minus mg2. And there's a map here to this stratum from H3G, which is the moduli space of degree 3 covers C2P1. And this map is actually an isomorphism when the genus is at least 5. And there's work of Patel and Vakil, which says that the Chow ring of H3G is generated by the pullback of kappa 1. And this is for G at least 4. In fact, Sam and I have shown as the beginning of our study of low-degree Hurwitz spaces that the Chow ring of H3G is actually equal to Q adjoin kappa 1 mod kappa 1 squared if G is equal to 4 or 5, and Q adjoin kappa 1 mod kappa 1 cubed if G is at least 6. At any rate, since the Chow ring is generated by kappa 1, and we know the fundamental class is tautological, if we use the push-pull formula, we'll see that all classes supported on this stratum are tautological. And when we put that together...
So can I ask one question?
Yes.
So, I mean, if you have such a degree 3 cover, how do you see that it's not an MG2 as well?
This is why I wrote that. I mean, so you can imagine you have a degree 3 cover and a degree 2 cover that can give you a map to P1 cross P1, where your curve has bi-degree 3, 2. And you will conclude that if the genus is sufficiently large, that this is impossible.
Uh-huh.
And furthermore, if the genus is at least 5, I claim that the degree 3 map is going to be unique. So I would then land by degree 3, 3 on this P1 cross P1, and that means the genus is at most 4. Yeah, are there more questions here? All right, so if we try to make this work for higher degree covers, this gets harder. And in fact, there can't be a neat argument like the one we gave here that holds for all G, because that would contradict von Zelm's result about the bielliptic locus in genus 12. But as in degree 3, we'd like to use the Hurwitz space. So HKG here is going to be the moduli space of degree K genus G covers of P1. And it admits a map to the moduli space of curves where we just forget the data of the map to P1. And the image of HKG is certainly contained within MGK. But in general, this map beta is not proper because the degree K line bundle that gives us this map to P1 could acquire a base point in the limit. But we can make this map proper by just throwing out all of the curves that have lower gonality. So here now I have HKG minus the pre-image of MGK minus 1 mapping to MG after I throw out MGK minus 1. And here, the image of this map in blue is MGK minus MGK minus 1. And this map is proper. So I can talk about push forwards on Chow groups. We have A star HKG minus curves of lower gonality. It maps onto the Chow groups of the image, which is MGK minus MGK minus 1, and I can push those all the way forward into MG minus MGK minus 1. And I'm working here with rational coefficients. So this first map from the Chow groups of the source onto the image is surjective. So if we want to show that all the classes supported on MGK are tautological, we just need to understand all classes upstairs on the Hurwitz space and show that they push forward to tautological classes. Now, the simplest way an argument like this might go is if all classes upstairs were generated by pullbacks of the kappa classes. But this is not expected to be true. And in fact, it's known not to be true when K is equal to 4 or 5 by work of Deoprkar and Patel. There's this statement goes by the name of the Picard rank conjecture. And it says that the dimension of the space of codimension 1 cycles on the Hurwitz space should be 2. So in particular, this group cannot be generated by the pullback of kappa 1. So to make this idea work, we're going to need a better understanding of intersection theory on low-degree Hurwitz spaces. So let me start by defining an analog of the tautological ring, but for the Hurwitz space. So the Hurwitz space comes equipped with a universal curve, and I'll still denote this map by F. And that curve admits a universal degree K map to this script P, which is my universal P1 bundle over the Hurwitz space. And we'll denote its structure map by pi. Then we'll define the tautological ring of the Hurwitz space to be the subring generated by all classes of the form F push forward of some power of the first Chern class of omega F times alpha pullback of some power of the first Chern class of omega pi. So basically, I have two families of curves now, and I can build classes out of either of their relative canonicals. So here's an example of the classes we can make in codimension 1. So maybe first we'll just take powers of C1 omega F. If we do that, then this class is just the pullback from the moduli space of curves of kappa 1. The next class I've written here is if we take one copy of C1 omega F and one copy of C1 omega pi, and I'll call this class epsilon 1. And the last thing you might think to do, which is take just a power of C1 omega pi squared, that actually turns out to just be 0. So the codimension 1 tautological classes are generated by these two classes here. Now, I also want to tell you about two other naturally defined classes on the Hurwitz space in codimension 1. And these have a rather different description. So these are the two ways for a cover to not be simply branched. So on the left, I have a picture of a curve with a point of triple ramification. So the closure of that is a divisor in the Hurwitz space, and I'll call that T. And on the right, the other thing that can happen is that two points of ramification can come together to live in the same fiber. And the closure of that locus is also a divisor in the Hurwitz space. And work of Deoprakar and Patel shows that T and D are tautological and independent. So this means that R1 of HKG, I can take as a basis either the pullback of kappa 1 and epsilon 1, or T and D. So in particular, this means that the dimension of R1 HKG is 2. So the Picard-Rank conjecture becomes equivalent to the statement that all codimension 1 classes on the Hurwitz space are tautological. Now, this perspective with these geometric classes is useful to us because of a theorem of Faber and Ponderoponde, which says that the push forwards of T and D to the moduli space of curves are tautological. And similarly, the push forwards of other ramification type strata are tautological. So here, like, for example, covers with a point of quadruple ramification would be an example of one of these other ramification type strata. This one has codimension 2.
By the way, one might also ask about push forwards of products of those things. Is the same thing?
Yeah, so that's a good question. It's related to something I'm about to say. I think in general, if you take products of these ramification type strata, it's not clear if their push forwards are tautological. But for example, if you just want to intersect T and D, I think you can say that the support of the intersection of these two divisors actually has codimension 2, and you can describe it explicitly in terms of ramification strata. But I think this becomes more complicated in higher codimension. yeah, so that's actually a great lead-in to the result I want to state next, which is that using this theorem of Faber and Ponderoponde together with quite a bit of work understanding the tautological ring of HKG for K equal to 4 or 5, Sam and I proved that the push forwards of tautological classes on the Hurwitz space are tautological on MG. And this argument goes by way of the theorem of Faber and Ponderoponde. So in codimension 1, we already know that by the work of Deoprkar and Patel, that R1 is generated by T and D, and those push forwards are tautological. But for our higher codimension cycles, I want to say a few words about the steps that go into this study of the Hurwitz space. So first, we found a minimal set of generators for the tautological ring. And we further found all relations among these classes in codimension up to roughly G over K. And then we showed that the classes of certain ramification strata generate all tautological classes as a module over Q adjoin kappa 1 and kappa 2. But I think this gets back to Bert's question. So you can't necessarily just multiply ramification strata, but what we found is that if you allow yourselves coefficients which are polynomials in the kappa classes, then a certain list of ramification strata actually generate all tautological classes. And then using the push-pull formula and the theorem of Faber and Ponderoponde, we can see that the push forwards of all tautological classes are tautological. And for applications, it's convenient to describe these classes we know push forward to tautological classes as tautological instead of as how they relate to ramification strata, because we'll be able to see that certain classes are tautological more readily. So given this theorem, our new goal is then to show that all classes upstairs on the Hurwitz space minus the curves of low organality are tautological. And we succeeded in proving this in several cases. So when the gonality is 4 and the genus is 7 or 8, and when the gonality is 5 and the genus is 7, 8, or 9. In the case when K equals 4 and the genus is 9, we actually proved something weaker than this, and we needed some extra tricks to show that this was sufficient still to see that all classes push forward to tautological classes. So the basic method of attack in all these cases is to stratify the Hurwitz space by the splitting types of some associated vector bundles on P1. And I'm going to explain this a bit in the rest of the talk in the case when k equals 4. It turns out that the case k equals 5 is actually quite similar in flavor, just a bit more complicated to explain. And the reason for this similarity is because we rely on some explicit structure theorems for covers up to degree 5. And these structure theorems for low degree covers don't seem to readily extend to covers of degree 6 and beyond. So you might be curious, how did we get this last stratum when the genus is 9 and the gonality goes all the way up to 6? And for this, we had a rather different flavor argument. There's some work of Mukai, which shows that this stratum of hexagonal genus 9 curves is actually a quotient of an open subset of a Grassmannian by a projective symplectic group action. And I'm not going to get into this in this talk, but actually, once you have this beautiful result of Mukai, this last stratum turns out to be quite a bit easier to deal with than the cases when k equals 4 and 5. So curves of gonality 4 and 5 was really where the bulk of our work was. So I'll also pause here for a moment if there are any questions.
Maybe one question. So I mean, this counterexample with bielliptic, with the bielliptic locus in MG, does this also give a counterexample in the Hurwitz space?
Yes. So you need to know, I think, a few more things, but yes, you can turn this fact that there's a non-tautological class on M12 into a proof that there must be a non-tautological class on H412. Yeah. More questions? All right, so now I'll get into some of the details for covers of degree 4. So let's say we have a degree 4 cover, C to P1. We can look at the 4 points in a fiber over a point on P1. And we can ask, where did these go under the canonical embedding of C into PG minus 1? And the geometric version of Riemann-Roch will tell us that these 4 points span a linear space of dimension 2. And as we move our point across P1, these 2 planes will sweep out a P2 bundle over P1. So that's the projectivization of some rank 3 vector bundle. And I can actually tell you what this rank 3 vector bundle is. There's a natural map from the structure sheaf of P1 to the push forward of the structure sheaf of C. And the alpha push forward of OC is a rank 4 vector bundle. So the co-kernel here is a rank 3 vector bundle. And it turns out to be equal to our rank 3 bundle mentioned here. And you can show using Riemann-Roch that the degree of this rank 3 vector bundle on P1 is G plus 3. Now there's another vector bundle that we can associate to this cover. And it comes from looking at the 4 points in each of these P2 fibers. So it turns out these points will have the property that no 3 are collinear, because that would correspond to the case when I have a degree 3 map plus a base point. And we're not allowing base points here, just honest degree 4 maps. So these 4 points will actually be the complete intersection of 2 conics. So they determine pencil of conics in each fiber. And that's the same as the data of a section eta of H naught of some rank 2 vector bundle tensor the relative O of 2. And I can write this also as H naught on P1 of F alpha dual tensor sim2 E alpha. And it turns out that the degree of F alpha will also be G plus 3. So what we want to do now is cut up the Hurwitz space according to the isomorphism type of this pair of associated vector bundles, E alpha and F alpha. So I'll explain this in the example when the genus is 8. So here, the degree of E and the degree of F are going to be 11. And these are vector bundles on P1. So they're going to split as a sum of line bundles. Say E is O of E1 plus O of E2 plus O of E3. And F is going to be O of F1 plus O of F2. So I made a table here of the pairs of splitting types that can occur for genus 8 degree 4 covers. And in this second column here, I'm going to list H1 of end E plus H1 of end F. And this quantity is called the expected codimension. It's something that measures how special are the splitting types viewed in the moduli of vector bundles on P1. And then it turns out that the codimension of this stratum in the Hurwitz space is given by the expected codimension minus a correction term of H1 F dual tensor sim2E. So in the first row, we have splitting type 3, 4, 4, and 5, 6. And these numbers are as close together as possible. So we call these splitting types balanced. And the expected codimension is 0 in this case. This is how we generically expect our vector bundles to behave. And it also turns out to be the general behavior on the Hurwitz space. There's no correction term in this first row. In the second row, on the left, the bundle E has become unbalanced with splitting type 3, 3, 5, but F is still balanced. And on the right, E is still balanced, but the splitting type of F, 4, 7, is unbalanced. And in both these cases, when I add up the H1 and E plus the H1 and F, I get 2. And these are not yet so unbalanced that there is a correction term. So the codimension in the Hurwitz space is also still 2. But when I get to the third row here, both E and F are now unbalanced. And we add up the expected codimension, we get 5. But there is a correction term here of -2. So the actual codimension in the Hurwitz space is 3. And then on the bottom row, we have even more unbalanced bundles. The expected codimension is 12, but there's a correction term of -10. So this actually occurs in codimension 2. So the way I want you to think about this is in terms of this picture here. There's a map from the Hurwitz space to the moduli space of pairs of vector bundles on P1, where we send a cover alpha to the pair E alpha, F alpha. And these correction terms correspond to when the fiber dimension is jumping in this map. So I'm going to analyze this stratification now in 3 steps. So first, I'm going to look at something we call the good open. And this is where there are no correction terms. So these are the covers alpha, so that H1 of F alpha dual tensor sim2 E alpha is equal to 0. And there's no fiber dimension jumping here. And it turns out that this locus actually looks like an open inside a vector bundle over this base, B circ, which is the moduli of good pairs of E and F. And this means that the Chow ring of the base surjects onto the Chow ring of the good open. And we were able to construct this base as a global quotient stack. And that gave us generators for the Chow ring of B circ. And we could show then that those generators were all tautological. So all classes supported on the good open are tautological. Step 2 is we're going to throw out the curves that have lower gonality. So it turns out that all of the covers in this purple stratum for splitting type 15529 actually are of the form a 2-to-1 map to P1 composed with another degree 2 map of P1 to P1. So this entire stratum gets sent into the hyperelliptic locus when we map to the moduli space of curves. And we already know everything there is tautological. So we can throw out this purple stratum. But when we do, there's still another stratum left, which is for splitting type 2, 4, 5, 4, 7. So we knew there was going to be a challenge somewhere, and this is it. And I think it's interesting to note that this has a relationship with the bielliptic locus. So the bielliptics can be found as a certain divisor here within this stratum. You will find all curves where this degree 4 map factors as a 2-to-1 cover of an elliptic curve with a 2-to-1 map of this elliptic curve to P1. So this dark orange here is sent exactly into B8, which is the bielliptics. So the final step is to study this stratum that remains. It's outside of our good open, but we didn't get to throw it away because of gonality reasons. So there are 2 steps here. We need to show that the Chow ring of this locally closed stratum is generated by the restrictions of tautological classes. And we want to show that the fundamental class of this locus is tautological. And it's enough to do the latter after throwing out the curves of lower gonality. So then we can use the push-pull formula to see that all classes supported here are tautological. So the key to part A is to realize that sigma is actually an open inside of a quotient of affine space by a group action. And then we can use equivariant intersection theory to get generators and excision on its closed complement to get relations. My favorite step is actually part B. We have to show this fundamental class is tautological. And to do this, we make the following 2 observations. So first is that sigma is the only stratum where the rank 3 vector bundle has splitting type 2, 4, 5. And the codimension of sigma, which we found to be 3, is equal to H1 of end E. So this means even though sigma might seem like it occurs in the wrong codimension, when you think about it in terms of the pair E and F, we can actually think about it as a splitting type locus just for the bundle E. And when we do so, it occurs in the expected codimension. This means then that we can compute its fundamental class by certain degeneracy formulas. And these will come to us in terms of pi push forwards of polynomials in the Chern classes of the universal E. So here, script E is built over this universal diagram as alpha push forward of OC mod OP. dual. And it's not hard to see that such push forwards are tautological. And it turns out that this same sort of miracle happens in many other cases, where it looks like a stratum has the wrong codimension when you view it as a pair splitting locus. But when you view it as a splitting locus for a single bundle, it occurs in the correct codimension. So then when we put together these three steps, so first was looking at the good open, second was throwing out curves of lower gonality, and third, dealing with what's left. We're able to show in the cases listed here that the Chow ring of the Hurwitz space minus the curves of lower gonality is tautological. So I want to end with a brief summary. A good slogan for this talk might be stratify until you have nice pieces. So we start off by stratifying the moduli space of curves by gonality, and then we further stratify the Hurwitz space by the splitting types of some associated vector bundles on P1. And the thing that allows us to move from the locus of curves of fixed gonality to the Hurwitz space, which is nicer, is the fact that push forwards of tautological classes are tautological. There is a trade-off, though. When you cut up your moduli space into more pieces, it means you need to know more fundamental classes. But we have a tool to find these, which is degeneracy formulas. However, these only work when your degeneracy locus occurs in the expected codimension. And this turned out to be the case for us by some coincidences of small numbers. So these are the main ideas that went into our proof of the main theorem, which is that the Chow ring of MG is tautological for G equal to 7, 8, and 9. So thank you, and I'll take questions.
Are there questions for Hannah?
Yeah. Can I ask?
Yes.
There's maybe this is a side question. So there is a world where bielliptic would be considered tautological, namely if one works with instead of just the Chow rings of moduli spaces as themselves, but the Chen-1 Chow rings or Chen-1 cohomology rings. So these are the orbifold cohomology rings that take into account automorphisms. So I don't know that they were studied beyond genus 2, but do you see any way of proceeding, maybe throwing in curves with automorphisms, etc.?
I'm not really familiar with that. I think it sounds very interesting. Yeah, I think it's kind of crazy that this bielliptic locus is not tautological, and maybe that suggests there are different notions we should use of tautological.
Can I ask? I mean, how much of this program works for genus 10?
That's something we're working on right now. So it turns out that this sort of coincidence of small numbers I've been talking about happens for the stratum that corresponds to the bielliptics. And in genus 10, the bielliptics completely fill the stratum that they occupy. But there are some other strata where, you know, you add up H1ND plus H1NF minus the correction term, and it's equal to neither H1ND nor H1NF. And we would need some other argument to know either that the push forward of its fundamental class to the moduli space of curves is tautological, or that it's, or the stronger thing would be if the fundamental class is tautological on the Hurwitz space. So those are, yeah, questions we're thinking about now.
Is it known in genus 12 if there are sort of other kinds of classes which might not be tautological? Are there sort of, like, is it thought that the bielliptic ones are really the only example there, or that you should see actually lots of different kinds of non-tautological classes, and the bielliptic ones just happen to be the ones that were found?
Yeah, I don't know. I think that's also a good question. And, you know, regarding, you know, genus 10, 11, maybe up to 12, I think that the program that Sam and I have developed, even if it can't show that all classes are tautological, should be able to give some sense of how far is the Chow ring from being all tautological. Right. To be able to say something like, well, we didn't find the fundamental class of this thing, but, you know, that's going to introduce at most one new non-tautological class or something. So yeah, I think that's also an interesting question to explore.
Can I ask which of these spaces are rational? So does it have to, like, I guess for small g, they're rational and the geometry is simple. Are these all non-rational?
So the Hurwitz spaces in these low degrees have these really nice descriptions in terms of just, you know, quotients of basically an open subset of affine space. And so I think, yeah, this should say some things about this. I don't know the answer off the top of my head, but.
Is there something about 11 which is a bound for like unirationality of those spaces, or am I confusing it with something else?
I'm not sure, but I think, yeah, that's a good question, as like, you know, how does the type of these spaces relate to all of this? Yeah, I think that's an interesting question.
Are there other questions for Hannah? Okay, well, if not, maybe let's thank Hannah again. And there will be a gathered